So, good morning. Good morning to you all in this edition of Studio Offshore Energy by TKI Wind op Zee. And in this event, like the other Studio Offshore Energy events, we present the results of research projects that are interesting to a wider community. And this time, the topic is speed rock dumping. And we have in this edition a presentation from about the research from Yorick from Deltares. A special welcome to you, Yorick, and please be aware that you are able to ask questions also about the presentation that will be given shortly in the chat. Yeah, I would like to immediately start with handing over to Yorick to present some of the research results from the RED project, as it's called. Yorick, can you start your presentation? You are muted, Yorick. We can't hear you.
Gotcha. Thanks.
That's much better. Thanks.
Okay, thank you. Thanks for the introduction. And well, I believe I have a relatively short time to tell you a lot of information. So I'll get started right away with the presentation of this piece of research that we completed in 2021 together with Seaway7, Scanmothering, and Rohde Nielsen. And when we started this research, Seaway7 was still offshore heavy transport, and I'm not 100% sure, of course, if this research inspired the takeover by Seaway7, but well, I would like to get started with presenting the research. My name is Yorick and on behalf of Deltares, I will present this piece of work. So here we go. So a bit of background. We investigated very basically rock dumping in offshore environments with the application for scour protection installation, of course. And the aim of this research was really to generate and improve understanding of the behavior of the dump of a wide graded rock dump during falling, but also during heap formation, with some central questions. And they may sound trivial, but do we use a fall pipe, yes or no? Do we let all rock fall on a single location, yes or no? And by this understanding, can we assess the impact of different dumping strategies, production rate, external forcing? And we did that via a hybrid modeling approach, meaning that we simply combined various sources of modeling. In this case, a physical scale model and a numerical CFD modeling. So we did a combination of various experimental conditions for numerical model validation, and then we further developed that numerical model after calibration validation for field application. So we applied the numerical model to assess conditions on a field scale. So I'll first zoom in a little bit on the physical scale model experiments, move on towards the numerical developments that we did, and I'll then bring it all together in some general conclusions. So we performed physical model tests in one of the facilities at Deltares. We used a 55-meter long flume, and that we divided in a couple of dumping spots so that we could do a large number of tests in a row. And in all these locations, we performed a different experimental configuration. So this is what the setup looked like. We had a series of cameras in front and a movable rock dumping installation, and we mimicked the dumping of rock via rock sliding down a metal chute. And that turned out to be quite tricky, actually. And we needed to be a bit creative. And this is going to be loud, by the way. We spent a lot of time. Let me see if I can mute. I hope this worked. We spent a lot of time trying to get the rock to slide down from the chute in the proper way. So we spent a lot of time trying to calibrate the production rate of rock, so how fast does the rock end up in the water, and it worked quite well. So there's a couple of lessons I'm sure to be learned here. I haven't found them yet, but we spent almost a week trying to get rock sliding down a metal chute in the proper way, and the results were worth it. And so here you see the final configuration. So we needed that drill to get a steady vibration to make sure that the rock kept sliding down the chute. And then we had a couple of LED boxes to illuminate the rock plume. We had a GoPro for underwater footage, a high-speed camera in front of the rock plume to really get a good video of the motion of the rock during falling for analysis and for comparison with the CFD runs, and a handheld camera to simply measure the entire routine, also so that we can look back later if there were any specific details worth mentioning about the test. So I'd like to show one of the results of the images that we obtained from the high-speed camera, and of course I know that in reality we would use a full pipe, but here we can really nicely visualize what's happening when the rock plume is falling through the water. And this was also a very nice calibration case for the CFD model. So on the left, you see a plume falling with a steady production of 1900 tons per hour without any ambient current. And on the right, you see the same, but with an ambient current. And you quite nicely see the rock plume being disrupted. And if you look very closely, you see that there's heavier rock falling out of the plume on the left side, and that the finer material stays in suspension longer because it's falling slower. You really see a very clear disruption of the rock plume due to the impact of the current. And this is something that we could measure quite nicely as well. So the nice thing about this research program is that we also had a lot of opportunity to take additional footage. So this is a result from the underwater camera of approximately similar configuration. So on the left again, you see rock falling without an ambient current, and on the right you see a rock plume with an ambient current. And as you can see, for this left case, we still had some issues with aiming the GoPro to the correct location. So you only see the edge of the plume, and here we had it. We finally understood how to aim the GoPro underwater to get both the plume and the heap correctly. So of course, what you see is when there is no ambient current present, there's a lot of dust coming from the plume, and you see here a heap of rock forming, and every now and then you see some of the heavier materials slide down. So there's this continuous avalanching and growing of the plume. And here you very clearly see this disruption of the rock plume. So this distribution in coarser material here at the upstream side, and this very long tail of finer grained material on the downstream side. And this is quite a nice base case observation, and of course also a good motivation of why you should use a full pipe, of course. I'd like to move on to the next slide. So within the project, we also had some time to try out some more exotic analyses. And so we had the opportunity to really investigate the segregation during the falling, which we termed hydraulic segregation. But also to zoom in on the segregation during the heap formation process. And I'd like to very briefly point out the two methods that we tried without going into too much detail, but we used a PIV to determine the hydraulic segregation. So we followed the particles of the plume, and by subsequent images could determine the mean velocity of those particles, and that gave a measure of the flow field in the plume, and thus also the segregation in the plume. And we used image analysis, color recognition type of analysis to measure or get some sort of a measure of the segregation of the rock after falling. So you see a nice example of this. On the bottom, you see the original mixture, and from that we derived the percentages of red, green, and gray content. And on the right, you see the distribution after a rock heap has formed, and you see that it's completely different from the initial condition. So there's a lot of coarse material, for example, here on the outer shell of the rock heap. So a couple of things that we obtained from this first analysis of the physical tests is that you can quite clearly see this falling behavior and this disruption of the current. And that's if you increase the production rate of the plume, that disruption becomes less, and there is more of a group effect. So you get more of a plume behavior than individual behavior. And depending on the falling distance in combination with the flow velocity, it takes, of course, some time for these finer particles to segregate from the rock plume. So that could also help in optimizing your distance from the seabed when you use a fall pipe, for example. In terms of what happened in the rock heap, so the geotechnical segregation, so what happens when the rock hit the seabed. we saw that at some point when the heap is growing, a very interesting type of segregation starts to occur, where due to continuous vibration, the smaller particles sort of move in between the larger particles, and you get this structure of the heap where you have finer material on the inside and very coarse material on the outside. And then the coarse material keeps sliding and avalanching, and then that process continues and continues. So you get some sort of a heap structure with very coarse material on the outer edge and on the bottom, and finer material on the inner edge if you let it form into a very large heap. And there is an optimum there, of course. So if you stop dumping at the same location on time, you don't have this problem as much. So that means that we sort of know which situation to avoid in terms of developing the rock heap. And then using this CFD model, we can make use of an additional tool to obtain more insight into the falling behavior of the plume. And then we can really investigate the effect of various environmental conditions on a field scale, so that we use information from the physical experiments in combination with information from the CFD simulations to develop an optimal dumping strategy. And that's quite interestingly, you see here, for example, the result of one of the many simulations that we did. And here you see the D50 in the rock plume without a fall pipe. So you see with an ambient current. So you see that indeed this segregation that we also saw in the video, this coarse material on the left side and this fine material on the right side, that's very nicely represented by the CFD model. And you see that it leads to a very clear segregation of rock in the rock heap. And we should take this with a grain of sand, because the fluid mechanical part of the model is going quite well. The geotechnical part, that's not what it was developed for. So this still needs some work, but you can already see the impact of using a fall pipe on the segregation in the rock heap. And it doesn't prevent segregation fully, but it does limit it. And that's quite nice to see. So one of the things we did then is see, okay, but what happens when we have a moving fall pipe with an ambient current? And so what if we really try to mimic this dumping of rock in a field condition? And what we quite nicely saw is that for example, there's a really clear impact on the segregation by doing your rock dump moving along with the flow or moving against the current. So if you use that in a clever way, you can try to influence the segregation in your rock heap. So that's one of the examples of what we try to use the CFD model for. So some possible next steps. So from the laboratory results and those conceptual understanding of what happens during falling, but also during heap forming, and we can define some sort of boundaries with respect to your dumping strategy. So use a fall pipe or don't dump all the rock on the exact same location. So that's quite basic, but it's a start, because then we have a bit more dedicated conditions to use the CFD model in to assess, for example, that hydraulic segregation in the rock plume. And that's going quite well, the hydraulic part within the CFD model. And then you can sort of indirectly derive that is the segregation before hitting the seabed is acceptable or minimal. Then you could also deduct that if, as long as the rock's well distributed over the seabed, so if you don't dump it all on the same location, then perhaps the segregation in your dumped rock mount is also quite minimal. And that means that you can try to optimize dumping operations on site using real environmental conditions. And another nice step to do is, for example, to investigate what impact this could have on scout detection performance by using various strategies of rock dumping for a given hydrodynamic climate. I think one more video here. This is one of the conditions where we try to mimic a dumping operation, and it looks a bit shocky because this was, I think, either me or Nick holding the fall pipe and moving it by hand through the domain, to get an idea of, okay, can we prevent segregation by moving the fall pipe and make sure that we don't dump all the rock on the same heap. And this actually worked quite well compared to letting all rock fall on the same heap. The segregation is quite minimal in this condition. So this is just one of the examples of how to utilize these results. So that mostly concludes my part. And I now have one slide left for Julian, who was, when we started the webinar, still fighting with his audio. So I'm not sure if that fight has been successful for now, but otherwise I'd like to give the floor to Julian. And yeah, by the absence of if Julian remains in silence, then I think we can move on to the questions.
Hopefully you can hear me.
Yes.
Yeah, welcome, Julian.
Okay, thanks. Apologies for any background noise. I'm actually in the lounge of a train station, so there might be some voices in the background. So I'll be brief. A small team at OHT, which subsequently became part of Seaway7, have been working on this wide grade solution for a number of years, and part of the concerns that we had was, as I say, the potential segregation, because it's a wide grade system, which culminated in the research program which Yorick has just described to you. And the driver for both OHT and Seaway7 is to be able to carry out our core business, which is foundation installation, and perform the rock placement, the scour protection rock placement as well, which is always a part of the scope of work for that package. And currently we have to go to outside suppliers for that. And a second requirement, or if you like, byproduct, we have a fleet of now 6 heavy transport vessels, of which one of them here is the Albatross, and we, working with Voik, able to come up with a design to convert it on almost a project by project basis or a seasonal basis, to put some sidewalls in and a fast mobilization rock deployment system with a 50-meter fall pipe on it, to allow us to perform the vast majority of rock installation for principally monopile protection. And the key thing, this is only a DP1, so it has to be pre-installed. So the idea is to deploy the rock onto the seabed, and you see on the right-hand side that it was our initial thoughts were to do it in a single heap. And as we progressed with Yorick and the Deltares team, it was becoming apparent there was unacceptable segregation. So at the latter part of the program, we tried, as I say, moving the, as Yorick says, and I think it was your fair hand, Yorick, that was rotating the fall pipe to allow us to have a more even spread, and then the resulting segregation was acceptable. So whilst it was the results were not good to start with the original single heap, the final iteration that we did was a definite success. So that's a summary of the sort of background as to why the program was carried out, and we are still pursuing this as a potential technique to support our monopile installation activities. I think that
thanks for these reflections, Julian, and thanks for making it possible to come into this call while you're traveling. It's and I also see some questions in the chat, at least one. Maybe we'll take that question right away, Yorick. The question is, did you compare the measured fall velocities against DNV RP C204, which provides guidance on impact energies from falling objects against these rocks?
We did not compare it to that specific guideline from DNV, but we did, of course, compare or calculate on beforehand what fall velocities we would expect, and did compare the PIV results with the CFD results for consistency. And then what's quite interesting to see is that if you really lower your production rate, you promote this more singular behavior, and then the average falling velocity you see is the fall velocity of the average grain size in your grading. Whereas if you increase that production rate, it converges more towards the fall velocity of the largest rocks in your grading, and that is consistent with previous research findings that we found in literature, and there aren't many, but they are available.
Yeah, thanks for this. And we also have Harm Verheul from Van Oord in this call. And welcome, Harm.
Yes.
And we also ask you to give your reflections on what you've seen in the presentation from Yorick and the comments from Julian.
Yes, well, thank you, Yorick and Julian, for this presentation. And well, I received the slides beforehand, and I had some questions, and you clarified a number of things which moved away the grass for some of the questions I had. But one of the things that stuck with me is if you're dumping rock on the seabed in a not so accurate manner, and then you're going to relocate those rock with some sort of machinery. I think a big difference that then starts to occur is usually when you dump the rock on the seabed, they penetrate into the seabed and you get a sort of a sandy rock foundation. Once you start to move those rock, I think there are a number of things you should start to look at in terms of residual settlement of the rocks, etc. and so on. Is that something that you've also taken a look at?
Short answer, no. Longer answer, it's a good point, and I do agree that indeed if you're going to redistribute a big heap, then there will inevitably be differences compared to the more accurate placement. The primary aim here was to assess the impact on segregation, because also that was one of the main questions, of course, from Julian's side. That okay, we have this wide graded mixture. What happens to or what's the impact on segregation? And then at some point we also realized that there are very limited guidelines on segregation in general. So that's why we focused a bit more on segregation and not indeed so much yet on seabed impact and what happens after redistribution. I think that's indeed a logical next step.
Absolutely, as the main concern, because it was a wide grade, was does it segregate, and our initial concept of having a single heap did produce an acceptable segregation. But now with the spiral or the zigzag method of deploying the rock and then leveling it after that, we should start to look at some of the potential issues, which, as you say, might be a slightly different profile of penetration and settlement as a result of both moving the material around, but also obviously running over it with a 40-ton subsea excavator. Although now with the spiral profile or the zigzag profile, we're proposing the actual amount of rock that you have to move, or the distance you've got to move it, is much less. So there's much less repositioning than with a single heap where you have to drag it all from the centre and out to the outside.
Yeah, so a lot of opportunity for further research as well, I take from this. And I also had a question about the effects or the impact of the research on the practice of installing scar protection. And you mentioned, Yorick, that one of these effects could be the optimization of the process. And my question to Julian is, do you anticipate a real speed up in terms of installation resulting from this research?
It's not significantly faster in terms of days. Obviously, we're using two spreads because we have the initial pre-installation and then the levelling. And certainly projects we're working on now, there's issues, as most people will know, with piling through rock. So we're quite often using a donut technique where we go along and do we leave a thin layer to pile through with the monopile and then go back and fill that in at the end. And one really rather important thing that's come as an aside for this in terms of a subsea excavator is there are other opportunities to do, if you like, cleverer things with the rock in terms of putting the inter-array cable underneath the rock and filling in the V-trench on top. And also potentially using the scan machine or another system to fill in the donut. So you actually put all the rock down, but rather than having to go back in with a DP2 smaller vessel and fill in the donut, or fill in the V trench, you can actually just reposition that rock after you've put in the monopile and the cable. So there's other potential applications for this twin vessel approach, and the overall cost basis of the vessels involved compared to dedicated rock placement vessels, we believe is commercially competitive.
Yeah. Well, thank you. Yeah, and Harm, did you have any, say, further questions, for example, about the application for yourself of these results?
Yeah, well, one of the things that's also then some further research that could be really interesting, I think, is if you usually we see that you dump 2 different rock ratings for one monopile foundation, and if you have some subsea asset that's able to move the rock, you might do some optimization of those rock placements. That's basically not possible with a normal fall pipe system or a normal placement vessel. So in that sense, I see some advantages, but yeah, as Julian said as well, the speed is probably comparable to what we do, and that's also what I figured when looking through the presentation. And yeah, then whether it's commercially viable, I have some questions about that, but I think this is much more to think of to talk about the technical side of things. And I think there are a lot of advantages on doing this, and as Yorick said, you can maybe do some optimization with the current hydraulic conditions to move your fall pipe in a certain way to make a beneficial use of this of the segregation. But yeah, operationally, that's going to give a lot of headaches as well, I presume. So yeah, it's you can. I think I don't really have a question, and at least not okay, a big one. Yeah. But a lot of thoughts of like maybe in this direction or in that direction would be nice to have a discussion about it maybe. Yeah. But
well, thank you for this, and maybe a short question to Yorick, leading the research from Deltares. What do you anticipate as next steps for yourself in this area?
I think there's then 2 different tracks. One what's scientifically interesting, or what's that could be seen more as a hobby. And then for one, we very much enjoyed, for example, the behaviour analysis of the rock plume, and that's more of a experimental technique development. But a rock plume is quite a nice, let's say, base case to do this kind of development. Absolutely very uninteresting from the commercial point of view, I guess, but scientifically extremely interesting. And from a commercial point of view, one of the things that would be or for me very interesting is indeed to see if we can further develop this experimental routine and take that into account also when doing our scour protection research, and actually take into account this rock dumping or the real installation of rock compared to how we apply it now, very cleanly and neatly without any let's say tolerances or without any segregation. And that for me would be very interesting to also be able to quantify the impact of a full installation on actual performance of scour protection, and maybe the outcome of that it's within the margin, and then it also means that we don't have to look very much more detail to segregation, and we say, okay, it's current practice is highly acceptable. But if it does have a very big impact, then I think looking into impact of segregation or into segregation itself would be a very reasonable thing to do.
Thank you, Yorick. And this also brings us to the end of this half an hour of Studio Offshore Energy from TKI Wind op Zee. I want to thank Yorick Broekema from Deltares very much for the presentation of his research result, and Julian Stewart from Seaway7 for his comments, and also Harm Verheul from Van Oord for his reflections on this research. And of course, I want to thank the audience very much for being present at this early moment of the day. I wish you all a very, very good day and look forward to seeing you again in the next edition of Studio Offshore Energy. Thank you.